Thank you very much for the introduction, and good afternoon, everyone. I'm Matthew Ames. I'm currently a postdoc at the Institute of Statistical Mathematics in Tokyo, working with Professor Tomoka Matsui and continue to work with my former PhD supervisor, Gareth Peters, in the UK. So in fact, Gareth and Tomoko are the authors of this set of lecture notes. So I understand there's a mixture of backgrounds in this room, but you all have one thing in common, which is that you want to use data to test hypotheses and make decisions about your experimental data. So over the course of the next two lectures, I'm going to focus on statistical inference, hypothesis testing, and decision theory. Okay. So today, we'll start by building up from the basics of probability. We'll introduce conditional probability and random vectors, and then we'll move forward to look at estimation of parameters, and following this, we'll look at hypothesis testing, which is the second set of notes that you've been given today. Okay. So fundamental to all machine learning, pattern recognition, and data mining is this concept of uncertainty. Now, where is the uncertainty coming from? So there's a number of sources. Firstly, coming from the observation process. So the fact that when you take measurements of an experiment, you have some measurement error. You never get the exact measurement. Secondly, there's also noise on the fundamental physical process, so random noise in your model. Thirdly is the fact that you only ever observed a finite sample of the real world behavior. So you collect a sample, but of course this is only a sample of what's happening in the real world, because if you had all of the data, then you don't need to do anything. You don't need to do any inference. You already have the entire population. Okay, so three sources of uncertainty. So in order to make robust optimal predictions, conditional on the observed state of the world, we need to understand probability theory and decision theory fundamentals. Okay. So the basic building block, going back 80 years, comes from Kolmogorov, who introduced this concept of a probability triple, where a probability space, or triple, serves as a rigorous mathematical grounding for the conventional idea of randomness. So what does this mean? So we have this triple, and it's a mathematical model of the real-world situation, for example, an experiment that you conduct, where we recognize that the outcomes of the experiment occur at random. So, for a given experiment, all possible outcomes which might happen are called the sample space, omega. So this is the first component of the triple. Then we have the collection of all possible events, where an event consists of many different elementary outcomes. So elementary outcome and elementary event and an outcome is the same concept, just referred to in a different way. Yeah. And then we have this third component of the triple, which is that we want to measure how likely each event is to happen. So we have a probability measure P for this. So our probability space presents a model for a given class of real-world situations, and we have to make a choice of this probability triple. Okay. So let's dig into a bit more detail of the triple here, and I'll give an example. So the sample space omega of the random outcomes is every instance of the real-world situation or run of the experiment must produce exactly one elementary event. Okay, So if we think of an example, okay, so say our experiment is rolling 2 dice. So one trial of the experiment is we roll 2 dice, okay? Okay. Okay, so omega is our set of outcomes, possible outcomes for this one trial. So we could have 1, 1, 1, 2, etc. So there's 36 possible outcomes here. Okay, so this is omega in this example. Now we have the sigma algebra, which we denote with a calligraphic F, which is the collection of all events. So this is one outcome, or elementary event. Okay, so our sigma is a collection of all events where an event is a set of 0 or more elementary events. So for example, one example of event could be that the sum of the dice is equal to 7. Okay. Okay. So there's many possible ways for this event to happen. In fact, there's six possible ways. So we can have 1, 6, 2, 7, etc. 6, 1. Okay? So 6 possible elementary events can lead to this more complex event happening. So we can say for E1, there's 6 possible elementary outcomes lead to this event. There's 36 possible outcomes in omega. So, I mean, it's quite clear to see that our probability, so here's our probability measure. So this is 1 in our probability triple. 2 is our sigma algebra, where E1 is just an example. So typically, this sigma algebra would be the power set of omega, which is, well, I'll talk a bit more about that later, but basically, you can think of it as all more complex events you can construct from this elementary set of events. So we can clearly see this in this trivial example that there's a 1/6 probability of this event happening. Okay, so they're the 3 elements of the probability triple. A few things to note on the sigma algebras. So the sigma algebra F is a subset of all events of omega, so we said that. F contains the null set, which is the empty set, which is denoted with this phi notation. Also, F's closed under complements. Not complements, complements. So A in F means that omega not A is in F, so the complement. F is also closed under countable unions. So for all AI that are in F, then the union of these AI, these events, is also in F. Okay. And we have many properties of the probability measure. So firstly, it's countably additive, and secondly, it measures the entire sample space to have 1. So this is, I'm sure you're familiar with this, so the probability of the entire sample space adds up to 1. Okay. So extending this idea to random variables. So any probability distribution defines a probability measure via this concept of Radon-Nikodym derivatives. But yeah, this is outside of the, I'm not going to go into the details of this in this introductory lecture, but you can have a look at what that means on Wikipedia, for example, if you're interested in some more theory behind that. So we have a random variable x is a measurable function, x mapping our sample space omega to another measurable space s called the state space. So this is our definition of a random variable. And now if we think about algebras, there's two types of sigma algebra we can consider. A countable omega, which typically means we can define f as the power set, as I was showing earlier, which is you can trivially show to be a sigma algebra and is in fact the biggest algebra, sigma algebra you can construct using this sample space. And then you have this uncountable omega, but this leads to problems if you just use the power set, and you have to consider something slightly different, such as a Borel algebra of omega. But yeah, we don't go into that in this lecture, so I'll skip over that. Okay, let's consider the basic elements of this probability triple. So intuitively, this probability P of E, probability of event E, should measure how likely this event is to occur. Going back all the way to 1933 with Kolmogorov axioms. So here we've listed the axioms of his probability measure. Okay. So for any element, you have a probability measure between 0 and 1. The probability of the entire sample space should be equal to 1. Then we have that if any infinite sequence of mutually exclusive, so that means that event 1 and event 2 can't happen at the same time, so mutually exclusive, then we just have that this is the sum of the individual probabilities. Okay, infinite sum. And similarly for a finite sequence of mutually exclusive events. Okay, some more axioms from Kolmogorov. So this is the probability of the complement of event E is just equal to 1 minus the probability of event E. So all of these are quite intuitive, I feel. And then you have the probability of the empty set is equal to 0. Now, if event 1 is a subset of event 2, then you should have the probability of event 1 is less than or equal to the probability of event 2. Okay. Again, then maybe this is kind of obvious. Then you have the probability of event 1 union event 2 should be equal to probability of event 1 plus a probability of event 2 minus the intersecting probability. So if they're mutually exclusive, then of course this is 0. So this is okay. And then by induction, you can extend this to an arbitrary number n of events. Okay. So they're Kolmogorov's axioms that form the building blocks of what we're going to discuss. But we note that these axioms only state the conditions an assignment of probabilities must satisfy. It doesn't tell us how to assign specific probabilities to different events in the sample space. So this is what we want to do from our data. So there's different approaches. So there's Bayesian and there's frequentist, and the most widely held approach being the frequentist approach. And this is what we'll discuss in this set of lectures. So the frequentist definition of probability is that if the experiment is repeated many, many times, in fact infinitely many times, then the proportion of time that event E occurs is its probability. So just this expression here. So P of E is a limiting probability, number of times E occurs over n. Okay. So this has the interpretation that the probability is proportional to the chance of occurrence of the event. And it's trivial to check that this satisfies all of the axioms we just looked at. But of course there's a problem with this approach, and that's that it's theoretical. We can't do an infinite number of repetitions of any experiment. And in fact, many experiments can't actually be replicated at all. So what's the probability it will rain tomorrow? We can't replicate that more than one time, let alone an infinite number of times. What's the probability of finding oil in this particular area on the map? So essentially, assigning probabilities in practice relies on prior knowledge of the experimenter, so some subjective beliefs, and or some assumed model of the probability distribution. Okay, so the simplest possible approach you could take is to assume all outcomes of the experiment are equally likely, where other more elaborate approaches would be to assume some kind of probability distribution, which we'll discuss later on. Okay, so the simplest approach is to assume equally likely outcomes across n possible outcomes. So from axioms 2 and 3, we see that there's np should be equal to 1, and simply we have that p is equal to 1 over n. Okay, so this is the outcomes probability. So for any event made up of k simple events, such as we showed in this example here. So event 1 is made up of 6 possible simple events. Then you can see that we have k equal to 6 and n equals to 36. Okay. So this is the classical definition of probability. And in order to work with this, you need to have some understanding of combinatorics, which is just a simple set of ideas. So multiplication rule, which is just that if the operation can be described as a sequence of k steps, and the number of ways of completing the step I is ni, then you just multiply each of the possible ways at each step point. So n1 multiplied to n2 to nk. So that's the multiplication rule. Then if you look at permutations, then you just have that the elements of a set in an ordered sequence results in this just taking a factorial of n. So the number of different permutations, if you have n elements, just n multiplied by n minus 1 to 1, so n factorial. Okay. And then combinations. So if a combination is a subset of the elements, so say you have 6 possible outcomes, then you choose 2, then you have 6 choose 2. So it would be C, 6, 2 in this notation. So you have 6 factorial over 2 factorial multiplied by 4 factorial. So you end up with 15 different combinations in that particular example. Okay, so that's the basics of probability. Now we want to extend this idea to conditional probability, which is thinking about the probability of an event happening given that some other event happens. So Kolmogor's definition allows this extension, simply. So if we say that every set A with non-zero probability defines another probability measure. So this is probability of B given that A, as happens, is equal to the intersecting probability of B and A. So B and A happen, divided by the probability of A happening. Yeah. So this is a fundamental concept in all of machine learning. And yeah, this is how you usually refer to it. probability of B given A. So if we have two events which are independent, you can see that the intersecting probability is simply the multiplication of the two probabilities. So we have three rules of probability here, which is a sum rule. So the probability of X is equal to the sum over Y, where Y is a member of this sample space omega. So the sum over Y of this joint probability. So this is the probability that X and Y happens. So this is the intersecting probability, just written in a different way. There's two ways you can refer to that. So if you sum over Y, then you get the probability of X. Okay, so that's the sum rule. We have the product rule, which states that the probability of X and Y is equal to the probability of Y given that X happens multiplied by the probability that X happens. Okay, that's straightforward. Symmetry, probability of X and Y is the probability of Y and X. Okay, so we can use these three rules to establish a relationship between conditional probabilities. And this small equation here is absolutely central to all of machine learning and is referred to as Bayes' theorem after the mathematician, well, Thomas Bayes. Okay, so we have the probability that Y happens given that X happens is equal to the probability that X happens given Y happens multiplied by the probability of Y divided by probability of X, where this denominator here is known as the evidence. Okay, so you'll use this very often when you're working with conditional probabilities and inference. Okay, so that's Bayes' theorem. So random variables. So we have a univariate random variable, y. So if we assume that y has this distribution, so capital F here is the cumulative distribution function, so CDF, which admits a density with respect to a Lebesgue measure. But actually, I'm not going to talk about Lebesgue measures at all here. Again, if you're interested, have a look here. But I think you have to take a course on measure theory if you want to fully understand all of the background behind that. So if it admits a density, this lowercase f, then we have the expectation of y is given by this integral of y multiplied by this density function lowercase f, which we call mu. And then we have the variance is just the integral of y minus mu squared evaluated with this probability density function f. Okay, and with some few steps of algebra, you can show that this is equal to expectation of y minus mu squared. So if you do a few small expansions, you end up with this difference of squares, which may or may not be familiar to you, depending on how much stats you've done. Okay. So basic properties of variance and covariance. So clearly the variance is non-negative because we have here, if we look at just the expression, we have that it's a sum of squares, so it has to be 0 or positive. The variance of a constant random variable is 0, which if you look at this, you can see. And so that the variance of a variable in a data set is 0 if and only if all entries have the same value. Okay. Now if we look at the variance of constant scalar a times y plus a constant b, then we see the variance is invariant with respect to changes in the location parameter. So adding b here doesn't change the variance. Just shifting your random variable doesn't change your variance. Okay. So, also, if you have uncorrelated random variables, then you see that the variance of the sum, of a finite sum of these uncorrelated random variables is equal to the sum of their variances. So x and y. The variance of x and y is equal to variance of x plus variance of y, plus 2 times the covariance. So if these are uncorrelated random variables, then of course the covariance is equal to 0 because they're uncorrelated. Okay. And then this idea extends with constants a and b as up here. Okay. So in general, for a sum of n variables, then we have this expression, a variance of y, where y is the sum of n different random variables yi. Just sum up their variances plus 2 times this sum of the covariances, where you just take the lower diagonal, so I less than j. Okay. So what is the covariance? So here's the definition for the covariance. It simply states that it's the expectation of y1 minus mu1 multiplied by y2 minus mu2. Okay. And similarly, you can expand that out to have this expression of expectation y1, y2 minus mu1, mu2. Okay. Yeah. So these are just some further properties of covariance. Okay. I think we've covered that. Okay. Okay, so they're the basics of probability, conditional probability, Bayes' theorem, and some properties of the covariance and the variance. Next, we move on to this idea of statistical inference, which is the core of the lecture series that I'm going to present. So this generally involves using statistical methods to draw conclusions and then make decisions about a population of interest. So we don't have access to the whole population, but we take a sample of observations of the population. Say we conduct an experiment, we have a data set. This is a sample from the entire possible world population. Okay, so this subset is our sample. So if this sample is effectively representative of the population, what we observe on our sample data set, we want to be able to say things about the whole population. We want to be able to generalize this to the whole population and therefore make test hypotheses and make decisions based on this sample. So yeah, there's a small note here. So populations are often described by the distribution of their values. So it's common practice to refer to a normal population when the variable you're looking at is thought to be a normally distributed variable. Okay, so that's just terminology. So in statistical inference, we focus on drawing conclusions about a parameter describing the population. So this might be the mean of the population, the variance, or say the proportion of individuals in the population that belongs to a certain class, or any other kind of construct. So you could say the difference in means of 2 subpopulations in your world population. Now, obviously, these parameters are unknown. Otherwise, we don't need to do any of this because we already know the answers. So the first part of the process is to estimate the unknown parameters. Yeah. So first we should note that random sampling is very important. So we want to ensure that the data we collect, our sample, is representative of the whole world population, and therefore we want to provide a framework for the application of probability theory to this problem of sampling. Of course, if the sample is not random, then all of our hypothesis testing and decisions based on our sample are flawed in some way, and we may lead to some incorrect decisions. So, what's a random sample? Okay. So, before we collect a sample of size n, the observations are modeled as random variables. So we have x1 to xn, so n random variables. And the definition of a random sample is that the set of observations, x1 to xn, should be, so the xi's are independent random variables in this x1 to xn. And that every xi in this set has the same probability distribution. Okay? So this is often referred to as independent and identically distributed, so IID. And we also apply this same term, random sample, when we talk about the set of observed values. So here, capital X, we typically use for the random variables themselves, and then lowercase x is for the observations. Okay, so we collect a sample, and anything we calculate using this sample is referred to as a statistic. So if we denote the unknown parameters of interest, theta, so this could be anything we just talked about, so mu or the variance or any other parameter of interest. So we refer to this as theta. This is a typical approach. And the only information we have available to estimate this parameter is the information contained in the sample. Therefore, an estimator of theta is a statistic, i.e. it's a function of the sample. We use our sample to make an estimate. So theta is therefore, so theta hat is the estimator of our theta. Okay. So yeah, it's a function h here of all of our random variables, x1 to xn. Okay. So now since it's a random variable itself, it must have a probability distribution. And this probability distribution is what's referred to as a sampling distribution. And the sampling distribution, this concept you need to become familiar with, is crucial to understanding all of hypothesis testing and statistical inference. Yeah. So the sampling distribution, which is the distribution of theta, generally depends on the population distribution and how big your sample is. Okay. So after we collect our sample, theta hat, which is a random variable, capital theta hat, it's a random variable, we have an estimate, which is lowercase theta hat. Okay. Always the same. Uppercase is the random variable, lowercase is our observation. Yeah. Okay, so in general, this is how we refer to them, our estimators. But since the mean and the standard deviation are so heavily used in statistical inference, they have a slightly different notation. So the sample mean is usually denoted by x bar and the respective lowercase x bar for the observation. And the sample standard deviation is usually denoted by S. Okay, so there are two notable exceptions for this. Okay. Right. Let's suppose that our random variable x is normally distributed with unknown mean mu and known standard deviation. Okay. So of course, we never really know the standard deviation, but this is our assumption for this going forwards, and then we'll relax that assumption later on. So from a random sample, a natural estimator of the population mean, mu, is just to take the sample mean. So add up all of the observations and divide by n. Okay? That's probably familiar to everyone. Now, since the sample is random, it should be representative of the whole population. And in some way, the population mean mu should be close to our observation x bar. Okay, so this is what this diagram's showing here. Population, take our samples, we have this sample here, calculate x bar, and we want x bar to be close to mu. But what do we mean by close is the important question. Now, this concept of the sampling distribution, which I just introduced, is going to answer this question for us. So we know that in this setup, each xi in the sample follows this normal distribution with mu and sigma. And they're independent since we have a random sample. So because of these properties and the fact that linear combinations of a normal random variable remain normally distributed, which is a nice property of the normal distribution, we can see that x bar, defined in this way, so the sample mean, has a normal distribution with mean given by of the expression 1 over n sum of xi, and then we can take the expectation inside the sum here, and we can see this is equal to the population mean. Okay, so that's nice. We have that the population, we have the sample mean on the expectation should be equal to the population mean, so that's what we want. And the variance, if we similarly calculate this expression, variance of this, take the n outside, so it's 1 over n squared, sum of the variances, then we get this expression, sigma squared over n is the variance of our sample mean. Okay. So the sampling distribution of x bar, so x bar, the sample mean, we have this is distributed and normally with a mean mu and variance. So standard deviation is sigma over square root of n if the population is normal. If the population is not normal, we still have the mean and variance, the mean and standard deviation, but we don't have this normality. Okay. So what we've shown here that x bar is a normal random variable centered around our population mean, so that's great. But with the spread becoming more and more reduced as we collect more samples. So this is nice. So we collect more samples, our estimate becomes more accurate. Okay, maybe this is kind of intuitive and obvious, but this is shows nicely what's going on here. So if you look at the plot here, you see with one sample we have this distribution. As you collect more and more samples, your variance becomes smaller and smaller around your mean. Okay. So now, since the purpose of conducting inference is to generalize from our sample to our world population, what we want to do is either estimate some parameters of our world population or test some hypotheses. So with regards to estimation, we have point estimation, which is just estimating one point, so estimate the sample mean. And then we have interval estimation, where we want to estimate some kind of interval around our sample mean, which we're confident in. So I'll come to this later. This is the concept of a confidence interval. So yeah, now we're going to explore some of the theory behind this and then work towards this concept of hypothesis testing. So firstly, we have point estimation. So we want to estimate an unknown parameter theta of a population. So let's start by looking at population mean mu. So again, we have this random sample x1 to xn. we select an estimator. And of course, this estimator is also a random variable with a mean, variance, and sampling distribution, like we just showed. So, for instance, we could use the sample mean, which we just looked at with this expression, and we derived these properties. Okay, but that's just one possible estimator that we came up with. So, and of course, it seems quite natural because you're probably already familiar with this. But there are many other possible estimators that we could use to estimate our sample, our population mean. So, for example, we could just take the first observed value and say this is our estimator for the population mean. Or we could take the average of the first and the last. Or we could take a weighted average of the first and the last. So, more generally, we want to understand which of these estimators is the best estimator and what does best mean. So certainly we want that our estimate should be close to the population parameter. What do we mean when we say closeness? So firstly, the population parameter is unknown. Otherwise, we don't need to estimate it because we already know it. And secondly, our estimator, any estimator we choose, is a random variable because it's based on our random sample. So we have to properly define what are the desirable properties of an estimator. So firstly, unbiasedness. So this is a definition of unbiasedness. So an estimator theta hat for theta is said to be unbiased if and only if the mean of the sampling distribution is equal to theta. Okay, so expectation of theta hat should be equal to theta. So on average, we should get the parameter we want to estimate. Okay, so this is intuitive. So if an estimator is not unbiased, then we have this difference. This is what we refer to as the bias, i.e. a systematic error in our estimation process. So far we've showed that our sample mean is an unbiased estimator for theta. And similarly, if we look at the other three estimators I just talked about, then we see that all of these are unbiased, unbiased, unbiased. Okay. So this property of unbiasedness is one of the most important properties, one of the most desirable properties, but not in every situation. Sometimes other properties become more important. It depends on what exactly you're trying to do further down the line. Okay, so just looking at unbiasedness alone doesn't give you a unique estimator to say, yep, this is the best one, let's use this one. So we need some further criteria. So how about we compare the variances of our estimators? So the sample mean variance we showed to be equal to sigma squared over n. But if we think about the theta 1 estimator, which is just taking the first value, we see the variance is sigma squared. So the variance of here is n times smaller than using this theta 1. Okay. So that means it's far more likely that taking the sample mean is going to be closer to the mean than just using the first value. Okay, this is obvious. Okay, it's a simple example, but it's important to understand this concept of variance of an estimator. So, yeah, a fact here. Estimators with smaller variance are more likely to produce estimates which are closer to this value we want to estimate. And so a logical approach would be to choose the unbiased estimator with the smallest possible variance, so the minimum variance. And we refer to this estimator as an efficient estimator, so efficient among the unbiased estimators. Okay. So that's the second property we're looking at for estimators. So if we think about these two properties, and we have an example here. So we have this analogy where each value taken by an estimator is a shot at a target. So obviously the bullseye here is our target value. If we look in the top left, we see that all of our values taken by the estimator are quite some way away from the target value. So this is high bias, but the variability of these estimates is very low. So this is a situation where we have high bias, but low variance of the estimator. Okay. Then we have B, where we have low bias because the expectation here is must be quite close to the target if we just look at the points, but the variance is very high. C, this is a terrible estimator because it's far away from the target but also spread out, high variance. This is the ideal situation. So we have low bias, so very close to the target, and low variance. Okay. Now if we take this concept of estimator variance to the limit, then we desire that the probability that the estimator lies close to theta approaches 1 as the sample size increases. So as we take more and more samples, then the probability that theta hat converges to theta is equal to 1. And we refer to this as consistent, so a consistent estimator. So of course you never have an infinite amount of data, but as n increases, you have this convergence to the theta. Okay. So this is easy to check for. So for our sample variance, if we just look at our variance, we see sigma squared over n. This clearly approaches 0 as n tends to infinity. So sample mean is consistent for mu. Whereas if we look at our other estimators, say all of them in fact, then we can see that as n tends to infinity, these do not tend to 0. So none of these other ones are consistent. Okay. So we have unbiasedness, efficiency, and in the limit of efficiency, we have consistency. Okay. So in general, and in most practical situations, we have that the sample mean is in fact a very good estimator. And it can be shown that the variance of no other estimator is less than that of the sample mean. Okay. Yeah. So there's a number of other properties of estimators that you can have a look for if you're interested, but I'm not going to talk about any further properties in this course. So we'll focus on these 3 ideas we introduced here. So for this reason, we're going to use the sample mean to estimate the population mean all the time. Okay. So although we know we have these nice properties of the sample mean, we still know that our estimate is an approximation of the population value theta. So for this reason, it's not very appealing to just report theta hat. When you do an experiment, if you just report point estimation theta hat equals some number, then what does that mean? We have no understanding of how close this theta hat is to theta. And in fact, we don't know this. Theta is unknown, of course. So for this reason, we move towards the idea of confidence intervals. So before we get to that, we need to understand standard errors. So we want to give this idea of how precise our estimate is. We use this idea of a standard error of the estimator, where the standard error is just the standard deviation of the estimator. And in fact, of course, in most situations, the standard error is going to be an estimated standard error. because if the standard error involves some unknown parameters you need to use to calculate the standard error, then you have to approximate those parameters to work out your standard error. So you end up with an estimated standard error. Okay, so you have this notation, sigma hat of subscript theta hat. Okay. So we're in this situation where we want to estimate the mean. We have our random sample of size n. We know that we have these properties, expectation and variance of our sample mean. So, but this sigma here, we don't actually know. So in practice, we need to estimate sigma before we can estimate this standard deviation here. So this standard error for x bar, the mean. So we have a natural estimate of the population standard deviation, which is just to use the sample standard deviation, which is this expression here. So standard deviation, where we have this 1 over n minus 1 value here, which I'll show why it's n minus 1 in a couple of slides. Okay, so we have this sample standard deviation, calculate that, and we can plug it straight into here, the numerator, in our calculation for the standard error for the sample mean. Okay. So when the estimator is normally distributed, if we make this assumption, we can be reasonably confident that the true value of the parameter lies within 2 standard errors of the estimate. Okay, so reasonably confident here means 95%. So this 68, 95, 99 rule just refers to the fact that if you have a normal distribution centered around mu, then 68% of the mass lies within 1 standard deviation. So this is 1 standard deviation, 1 standard deviation. You have 68%, and then within 2 standard deviations, you have 95%, well, all over the way here, 95%, and within 3, you have 99%. Okay, so if the estimator is normally distributed, and we take 2 standard deviations, we can be reasonably confident, this is 2 standard deviations, sorry, here. So we can be reasonably confident, i.e. 95% confident, that the true value of the parameter lies in this range. Okay. So this is what we're doing here is moving towards giving an interval of values for our estimator rather than just a point estimate. Okay. So, and even in the case when we can't assume this normal distribution, if we look at Chebyshev's inequality, then we see that if we use 4 standard deviations away from the mean, then we have 94% confidence interval. So 6% of the time is outside of this region. Okay. So these ideas are the basis of interval estimation, confidence intervals. So instead of giving a point estimate, which is just a single value, which is obviously is not equal to theta anyway, we want to give this interval. So let's look at an example. So this is from an old journal article about heat transfer. So thermal conductivity in Armco iron, if you're familiar with that. So we have these measurements of thermal conductivity. So it doesn't matter what the example is here. This is just data, the same as when you have some data, you're going to want to do some statistical inference about this and hypothesis testing. So it's trivial you can calculate the sample mean, add them up, divide by 10. There's 10 values here. Now we know that the standard error of the sample mean as an estimator for mu is given by this sigma divided by square root of n. We don't know sigma, and we never know sigma. So we need to use this expression, sample standard deviation, to calculate here, and we get this value 0.284 for this data set. So we plug all this in, and we have our standard error for x bar. So the sample mean is equal to this value here. Okay? Now, if you look at the two values, you can see that the standard error is small, relatively small here, 0.2% of the sample mean. So in some way, we can say qualitatively that this is a relatively precise point estimate of the true mean. We don't know the true mean, of course. So if we assume that the thermal conductivity is normally distributed, which I don't know whether we can assume that, and of course, making this assumption may be unrealistic. I don't know about this application. Then 2 times the standard error, we have just multiplied by 2, we have this 0.1796. So we have this interval around our sample mean here, plus or minus this 2 standard deviation. So we have this interval, 41.744 to 42.104. Okay? So if we assume normally distributed thermal conductivity, then 95% of the time we have this confidence interval. Okay? Now, if we don't assume normal conductivity, we use 4 times estimated error, as pointed out by the Chebyshev inequality, then we have this slightly wider confidence interval. Okay. So obviously here the term highly confident needs to be quantified. And this is the basis of confidence intervals. So the definition of a confidence interval, it's an interval for which we can assert with a reasonable degree of certainty or confidence that it will contain the true value of the population parameter under consideration. So a confidence interval is, so firstly you need to select confidence level before you collect your data. Set out your confidence level that you want to look at, and then you collect your data. Okay. So you measure the degree of reliability of the interval. So a confidence interval of level 100 times 1 minus alpha, so say alpha is 0.05, then you have a 95% confidence interval. Okay. So frequently the confidence intervals which are reported are 95%, 90%, 95%, and 99%. So the higher the confidence interval, of course, the more strongly we believe that the parameter lies within this interval. So we should expect that the interval should be larger if we want to be more confident, smaller if we use, say, 90%. Okay. Yeah. So in terms of interpretation here, we need to be careful. So this remark 2. So sometimes it's tempting to interpret this confidence interval for theta as saying that there's, say, 95% probability that theta belongs to it, which is not technically true, not exactly true. And in fact, this, say, 95% interval refers to the percentage of all samples of the same size, same possible size drawn from the population, which would produce an interval containing the true theta. Okay, so maybe I have a plot there. Okay, I'll come to that. a correct interpretation is that if we consider taking sample after sample from the population and use each sample separately to compute this 95% confidence interval, then in the long run, 95% of these intervals will capture theta. Okay. So to understand this, the key concept is to realize that the confidence interval is a random interval because you use a random sample to calculate the confidence interval. The confidence interval isn't some magical interval that you know, because of course you don't know any of the population parameters. Okay, so it's a random interval. So that once you calculate this confidence interval, the true value either belongs to it or doesn't belong to the confidence interval. So any kind of statement where you say, like, where you try and use probability instead of confidence level, doesn't really make sense. Okay, so this is the small simulation to show what was happening there. So if you take 100 random samples of size 100, here we see that 96 intervals of the 100 contain the true value. But obviously in practice we don't know this. This is just to understand the interpretation of what it means, confidence interval, random interval. Okay. Okay. So firstly, let's start assuming unknown mean but known variance, which isn't the case realistically, but we'll introduce that later. So we have this random sample, mu unknown, sigma known. So we have our sample mean, same as we had all along, and we can standardize this normally distributed random variable. So we get this z random variable, which is just a standardization of the sample mean. So x bar minus the mu, the population mean, divided by this standard deviation. So in doing so, we end up with a standard normal distribution. So normal distribution with mean 0 and standard deviation of 1. So if we want to calculate a confidence interval of level 95%, for example, then from our random sample, we have this random interval with these bounds L and U, which are of course themselves statistics because they're random variables. So the probability that mu, the population parameter, population mean, is between lower and upper confidence bounds is equal to 1 minus alpha. So say 0.95. Okay, so this is the diagram that we're looking at. So we have we introduced this concept, this z value, to allow us to use standard normal 0, 1 values in our calculations. And so we can write the probability that this random variable z, which you remember is calculated using our x bar, standardizing our x bar. So z, probability that z is between these quantile levels is equal to 1 minus alpha. So this notation here, so okay, look at the right one. So lowercase z subscript 1 minus alpha over 2. So say alpha is 5%, so 0.05. Then you take this quantile level, well, this value of z at the quantile level of 0.975, because you have a 5% alpha, and then you're looking at both tails, so you have 2.5% on each tail of the normal distribution. Okay, so that's how you calculate these z values. Just from, I mean, you can simply just look these standard normal distribution values up in tables in books. But of course, you're using MATLAB, so you can just use the simple command. Okay, so this expression is exactly the same as this expression here. So Z is equal to this value. So expanding this out, we have that the probability that mu lies between these two values is equal to 1 minus alpha. And of course, so we found these L and U, which are two statistics, random variables, that we're looking for. Okay. So if x bar is the sample mean of an observed random sample size n from a normal distribution with known variance, sigma squared, then the confidence interval is given exact. This is the confidence interval. It's just as simple as calculating this. Plug in all, calculate from your data x bar. You have n, however many samples. So here we're assuming sigma is given, and z is calculated a couple of slides ago. Okay, so all just calculation, quite straightforward. So since we have standardized with Z, we can look at these Z scores. So Z at 95% confidence, sorry, Z at 90% confidence, so Z 0.95, because you have 10%, so 5% either side, is equal to, so if we've centered our distribution, then we have this at 0, and the standard deviation is equal to 1. So we have 1.645. Sorry, here, 2 standard deviations. Well, yeah. Yeah, at 90%. So we have 90% confidence interval if we use the Z score of 1.645. So this is as simple as just plugging 1.645, 1.96, or 2.575 into this expression here to get the 90, 95, 99% confidence intervals. Okay. So we can, of course, see that these confidence intervals grow in length. Yeah, so inversely related to the confidence level. So what we want to do is have a short enough confidence interval so that we can actually make a decision. Because of course, if the confidence interval is huge and we have 99.99% confidence in this interval, but then this is not useful because we don't know where the parameter is over such a large range. So we want to be short enough for practical decision-making purposes, but also we want to have enough confidence that we're making a good decision. So one way, of course, to reduce the size of this confidence interval is just to collect more data. So in some situations, this may be possible, but in many situations, of course, you can't just collect so much data. It's expensive to collect data. Okay. Yeah. So we have this error E equal to the x bar minus mu. Okay. Okay. Yeah. So this is just showing that we have 95% confidence that the error will not exceed a given amount E when the sample size is this expression squared. Okay. Now we come to an important concept, which has been referred to as the unofficial sovereign of probability theory. It's quite strong praise. It's a remarkable result which basically says that the sum of a large number of independent random variables has a distribution that is approximately normal. So this goes back a long way to Abraham de Moivre and Laplace, and then the turn of the 20th century, Lyapunov. Okay, so I'll leave you to do some reading about the history of that. Okay, so basically what this says is that if we have a random sample from a population with mean mu, finite variance, sigma squared, then if x bar is our sample mean, then the limiting distribution of this expression, so this is x bar, so the sum up of x minus n lots of the population mu divided by the standard deviation, and then we have our scaling, has a standard normal distribution as n tends to infinity. So we don't prove this here, but you can look this up. It's not so long. The nice thing here is that xi, these random variables, are not necessarily normally distributed. So despite them not being normally distributed, we still have that the sample mean tends to a normal distribution as we collect more data. So this is great. So yeah, so all of this is just a standardization of x bar to get to a standard normal. So this means that the standard normal distribution provides a reasonable approximation to this distribution when n is large, which maybe we want to know how big n needs to be, but I'll show that in a minute. So as I just mentioned, the power of this central limit theory is that despite xi not being normally distributed, so any population distribution, discrete, continuous, then you still have this asymptotic property or approximate property when you don't have infinite data, which is always the case, of course. So some facts: the larger n, the better the normal approximation. Maybe that's intuitive. The closer the population is to being normal, so the closer xi is to normal, then the more rapidly your your sample mean approaches normality as n gets large. Okay. So here's just a couple of examples here. So if xi is uniformly distributed from negative root 3 to root 3, then n equal to 1 is the n equal to 1 is population distribution. So n equal to 2 is the red one. So as you take more and more samples, then you get much closer to the standard normal distribution, which is this pink magenta one. Similarly for exponential distribution, and in fact for a Bernoulli distribution with various parameters. Okay, so a couple of remarks. So the central limit theory is not only a simple method for computing approximate probabilities for sums or averages of independent random variables. It also explains why so many natural populations exhibit this normal distribution curve. So indeed, as long as the behavior of the variable of interest is dictated by many independent contributions, it should be at least approximately normally distributed. So for example, a person's height is a result of many independent factors, both genetic and environmental, which all contribute a small amount to the overall random variable. So the central limit theory guarantees that the sum is approximately normally distributed. Okay. So remark 2, we want to know how big n needs to be to have this, have a nice approximation to the normal. So this depends on the population distribution, but as a general rule of thumb, we can be confident if we have, say, greater than 30 samples, and in many cases, less than 30 is going to be a good approximation. Okay. So, furthermore, the central limit theory allows us to derive confidence intervals for mu in an arbitrary population. So of course these are going to be approximate confidence intervals, whereas before we had exact confidence intervals in a normal population. So if we have n large enough, then similarly we can say these expressions are the same as before, but here we have an approximate confidence interval. Okay. And thus it follows we have this same expression. All that's happened here is just change this to approximate. And we have this confidence interval here. Yeah, the terminology here is large sample confidence interval, since we require n large enough to be reliable. Okay. Okay. So that's the end of the 6 o'clock. That's the end of the first set of notes. So I think next week we'll start from hypothesis testing, so which we build on the ideas we've introduced here of statistical inference, and start to look at how we can formulate a test of a hypothesis, use our data to say whether we can reject this null hypothesis. But I'll introduce this next week. Okay. Thank you very much.